this bit here that's missing, the missing gap in the middle. And that's what it means by RMS. So RMS is true power. Peak power doesn't mean a lot because it's just measuring up to here, and it's not taking into consideration that the sine wave has got gaps in it. That's all that means, but let's stay with the convention there. So let's double click on the thing, and let's go to the magic number. Always work in tens if you can. So we're going to have 10 volts RMS. You'll notice there's other things in there like voltage offset. Leave that alone, because you don't really want to offset the voltage. So leave that alone, but that is what I was talking about earlier, where you can put it on top of the DC or put it back down to 0. That's what the offset is, but leave it alone. Just change that to a number you're comfortable with. Like I said, I like tens. Okay, so can we use a multimeter to do this? That's a loaded question. You can.
But it will show the RMS.
Yeah, that's right. So one of those multimeters there will give you a single value. So if I put 10 volts peak to peak in, and I put it into a multimeter, it's going to try and measure the RMS. In other words, the actual amount of power which is in there, neglecting the fact that it's going up and down. If you don't get that, don't worry, it's not that important. It's going to be much more meaningful if we can actually see the wave, right? Because we know it's there, we know that that signal generator or the AC source at the beginning there is making this wave for us. But now we've got an added complexity because we're putting it through a potential divider. Now remember what a potential divider does. It means that we can generate a voltage on the output as big or as small as we want. But not only can we do that with DC, we can do it with AC as well. So let's do that. Let's do exactly the same experiment that we did earlier, but instead of using a multimeter, and right over on the right hand side now, let's use an oscilloscope. Okay, so we're going into big boys and girls territory now. So we put the oscilloscope on the screen, and you can see it's got A channel, B channel, and external trigger. We're not going to use the external trigger for these purposes, and we're going to wire that up just like we did the multimeter, just like before. Okay, so we're injecting 10 volts RMS, and we've put it through a potential divider. Now at the moment, I would expect the amplitude to be halved. But to be able to do that, I'm going to do something, no, let's keep it simple to start with. Let's keep it simple and we'll just use one trace. So now if I run this simulation, remember the green button up the top there, let's just open up the scope and have a look first. So looking down the bottom here, it says time base, 10 milliseconds per division. So that means on the grid, in time, each one of those boxes is 10 milliseconds. And on the scale, each one of those boxes is 5 volts. Yeah? So now if I run this simulation, what can I see? Not a lot because we're not triggering very well at the moment. There we are, that's better. I forgot how to do that. Does that make sense? So I put 10 volts in, RMS, and if you look at that vertical scale, it says channel A, 5 volts per division, and it looks like I've got about 7.5, something like that in there, isn't it? So if I've got 7.5 on the top, 7.5 on the bottom, that's 15, and I only put 10 in, so where did the rest come from? Well, it's because it's RMS, basically, root mean square. But let's just stop that for a second. So if I go in here, can I change that from RMS? No, it won't let me change from RMS. So it's an RMS source, we're just going to have to live with that, unfortunately. Okay. So run it again, there it is, everything's fine. So now what I can do here is if I increase the size of R1, I'm going to drop more volts across R1. So R1 should control, or should reduce the amplitude of that sine wave according to the value that I assign to it. Let's do something else now which is also a bit clever. I'm going to delete, shut it down for a minute. I'm going to delete these here and do something which is very, very common when you do AC analysis. The first thing that you actually want to know is what you're putting in. So how can we see what we're putting in? Well, we could do that. And, all right, it's a bit messy, but the point is made. We can do that. So we can actually see what the source is. We're not worried about what's coming out the output at the moment. We can just see what's in the source. And if we run that, you can see that's what's coming in from the signal generator. Okay? Now let's wire up channel number 2, and we'll wire that to the output. So one is V in, the other one, this one here is going to be V out. Like so, yeah. And what I would expect now is 2 traces. I would expect one trace to be the input and one trace to be the output. Terribly wrong, by the way, but all I've done is connect the oscilloscope to the input and the oscilloscope to the output. And lo and behold, I've got 2 waves there. Yeah? So one of those, and if you do some measurements on it, you'll see that one, however you measure it, but peak to peak, is probably the way that most people would measure it, you'll see that one of those signals is half what the other signal is. That's what you would expect, right? Because you've done the experiment with the DC, and half the voltage is dropped across one resistor, half the voltage is dropped across the other resistor, and you're looking at the voltage in between. Yeah. So that's great. That rather reinforces the theory that we had before. So now let's do something quite radical, and let's make the output, say we want the output to be really small. Okay, now to me, really anything is an order of magnitude. So it's either multiply by 10 or divide by 10 is my definition of real. I mean, some people would tend to do it on 100 or whatever. But if I make that R1, say 10k now, what's going to happen? What's going to happen to my output? Well, bigger, hands in the air, hands down. Is it going to make the output bigger or smaller? I hear smaller. Do I hear bigger? Good, well I hope not, because the smallest have it. So now if I run the simulation, lo and behold, look, the output's tiny. So exactly the same as that. Nothing's changed. This applies to AC as well as it does to DC. It's a potential divider. Why is it so? Because resistors aren't reactive. They don't care whether it's DC or AC. They do the same thing for everything. That's not the same as is true for capacitors and inductors. They do care. They do care how fast it is. So now let's do the experiment the other way around. So, I've got 1k in there. Oops, I'm still running the simulation, always do that. And I put 10k in here. Okay, someone tell me what's going to happen there. Same thing is not the right answer. Because I'm still going to drop something across the 1k, aren't I? It's going to be nearly the same, right? Close to the same, yeah? I'll do another experiment in a minute where we'll just put a silly value in there so it is the same. But so there's the input, there's the output. Pretty close, right? with that 10:1 ratio the other way around. Now, if I want to make them pretty much so that they are exactly the same, well, what value of resistor do I need to make it exactly the same? Speak up?
No resistance at all, or like shorted out.
Yeah, 0. So if I put 0 in there, what that means is the input is the same as the output, so I get the same waveout, right? But if I put, it's uncommon to use 0 ohms, so let's just put 1 ohm in there. Let's put 1 ohm in there. Now 1 ohm, if you look at the ratio between 10k and 1k, and 1 ohm, they're so close to one another you're not even going to see it on the scope. You can't, they're superimposed on each other. They're so similar that you can't even discern. Okay. Does that make sense? So I think what you can do now is you can construct a potential divider. You can divide down, you can't go bigger than the input, because you need a higher supply range to be able to do that. But you can go smaller than the inputs, you can control it very accurately, because you've got equations to do it. You can control that output voltage, you can control it in DC, and you can control it in AC. What about frequency? So we've already said, so let's go back to, let's go back to 1k here.